and I'm from Ridgewood, New Jersey, and I am here to present a new method to explore the integer partition problem. Integer partition is a well-known difficult problem in number theory, and no solid solution has been found until today. I have used the linear difference equation and root of unity to successfully get the expressions for integer n when the group number is k equals 2, k equals 3, k equals 4, and k equals 5. This proves a close relationship between integer partition and the root of unity. With the analysis, it can be concluded that there will be an expression of u and k existing for any n and k, and we have found a method to further develop the expression. Also, this has provided an interesting method to do further research in this integer partition area. Integer partition is a fascinating category of mathematics with a long history and many applications. It has played a significant role in the development of number theory and has contributed to various fields such as computer science, physics, and music theory. The study of integer partition continues to be an active area of research and is likely to lead many new discoveries in the future. No solid solution has been found for any u and k until today. I am here to show you what a general solution for u and k would look like with our method. In number theory, a partition of a positive integer n, also known as an integer partition, is a way of writing n as a sum of positive integers. The goal of integer partition is to figure out the number of ways the number n can be broken down into k ways. For example, 4 can be broken down into 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 2, or 2 plus 2, or 3 plus 1, and also just 4. Repeats will not count, like 3 plus 1 and then 1 plus 3. For example, if you see 1 plus 1 plus 1 plus 1, the number n, in this case it's 4, can be broken down. On the next slide is an example of the number of ways u and k when n is from 1 to 10 and k is also from 1 to 10. Blank spaces are equivalent to 0 because when n is less than k, it's not possible to partition it. So this is a chart of what the top row is, what the value of k, and the column bottom is the value of n. So you can see if n equals 4 and k equals 2, you can see there are 2 ways. And this can go on for a very long, and it will keep getting bigger. As you look at it, you can see a lot of patterns, such as the first column is always 1, and the diagonal is also always 1. Using these patterns, we can find out a way to find any u and k efficiently, but there is still no solid formula until today. The linear difference equation is an equation that shows the functional relationship between an independent variable and consecutive values or consecutive differences of the dependent variable. To get the general solution for a linear difference equation, we need to first find the solution of the homogeneous equation first, and then get the solution for the non-homogeneous. The general solution is to combine the two solutions all together and find the constant coefficients to effectively solve the problem. What this means is we should find the solution of an equation that we already know the values of n and k because we have the chart, and that will help us find the general solution. This is where we use root of unity. As you can see in this figure, there is a circle divided into 4 parts and also divided into 3 parts. So root of unity is finding the angles So we all know that this angle, which is 90 degrees, because it's split into 4 parts, is 90 degrees. And also right angle. We could also express it as half of pi. And the other angle, which is like the circle is cut into thirds, you can express it as 2/3 pi. So these are the roots when the circle is divided into 4 parts and when it's divided into 3. You can see lots of similarities, such as this part and also many others, which will help us find a general solution. These are the 2 basic equations. For this is what we're trying to find, u and k, and that can be altered into this equation, un minus 1, k minus 1, plus u and k minus k. So here n stands for the whole number, and k stands for the group for partition. U and k is a number for integer n when we do k partitions. When k equals 2. For when k equals 1, as we saw in the chart, when k equals 1, everything is 1. So we can use that, and since using our method of root of unity, we can find that the formula for k equals 1 is just cosine 2n pi, which is otherwise equivalent to 1 always. So our method is using the formula for the previous solutions to find the next one. So for k equals 2, we use the solution for k equals 1 and add on some stuff to make it k equals 2. So if you solve the equation, you can find that un equals half of n minus a fourth plus a 1 to the n plus a2 negative 1 to the n. So what this means is that you take half of n, and if n is an odd number, you take half off. So if you see in the chart, when k equals 2, n is always, you can see that there's a pattern. N is always the u and k is always half of n, and then if it's an odd number, you take out the 0.5. You floor divide it, which means you only take the number part, not the decimal part. So you could see with 7, it's 3, which is 7 divided by 2 is 3.5, and you take out the half. So using this, and a1 and a2 stands for constants, which we can figure out because we already know most of the solution, the answers for k and u and k, because we have this chart, which helps. For k equals, also you could for k equals 3, you have the part from k equals 2. This part right here is also added into k equals 3. So we use the solution for k equals 2 to help us find the solution for k equals 3. And if you simplify it down, you can find that this is the solution for k equals 3. It doesn't look like it would give you a whole number as a result, but it does. So you could test it out if you'd like. This uses cosine and pi because it involves the root of unity from the diagram, you can see that 2/3 pi and 2/3 n pi. And yeah. Next, when k equals 4, we have this. All of this is from k equals 3. Like 1 over 12 and squared. And then we use that to help us find the solution for k equals 4. This is the ultimate solution for k equals 4. You can, so it is worth noting that when k equals 4, n is to the power of 3. And when k equals 3, n is to the power of 2. K equals 2, n is to the power of 1, which is the base of n. So that's one thing to know. And then it decreases by 1 each time, you see. And all of this, all the cosine and sine parts are all from root of unity, which all of these roots are lead to that. When k equals 5, as if we use this method, as the k and n get bigger, it will become far more complicated to solve it. So we plan on using computers to help us perform the mathematical expressions quickly. So, and if you see k equals 5, you can see the 4, k, n to the 4th, and n to the 3rd. You can see a pattern. So we use k equals 4. We use the solution for k equals 4 to help find the solution for k equals 5. But this is the solution for k equals 5. And also, all the cosine and sine parts are from the root of unity. And the rest, it's also worth noting that most of the terms in this solution are to help balance out the number. Like, for example, this number is to help balance out, to help us get a whole number as a result. For k, with any value, this is very complicated and will take a long time to be able to solve, but this is a rough idea of what it would look like. So you can see that there are lots of constants with a and b, which you have to be able to know the values of the u and k. Then you can find constants. And this is a general idea of what it would look like using our method, which will make it will look very complicated, and it's hard for a person to solve it, but it should be simple. Computers should be able to solve it efficiently. Conclusions. As shown in this paper, a new method to analyze the integer partition problem has been introduced. We have got some interesting results when k equals 2, k equals 3, k equals 4, and k equals 5, which have all been verified to be correct. We have found some interesting patterns, and although the calculation will become more and more complex when n and k become larger, we can still be confident to claim that there will be a formal expression existing to calculate the number of u and k, which is a big step in the journey of getting the final solution of the integer partition problem. The methods we use here are new and interesting, which can help other researchers in this field do more research. When the calculation is too much, we can just use computers to solve the problem, because we already know what we already know because of the chart what the u and k is if you know n and k. Thank you for listening.